Hello everyone, today I'm going to present our work on navigating demographic bias on machine learning models on social media. So first of all, I want to talk about a common problem in the social media. So assume we're training data is textual data from Twitter. So those are the tweets, and we are trying to build a machine learning model to make some predictions. But the problem is how can we know our machine learning model is fair without knowing the demographic information about users? So this is kind of, we have a training data, machine learning model, and some prediction labels. So in most real world data, the sensitive attribute is not always available. So we are not able to first measure the bias of machine learning models or improve the bias of machine learning model without access to the sensitive attribute. And then one of the solution we're going to present in this paper is that one solution to this problem is actually to infer the sensitive attribute from the training data. So in social media, it is possible to get information about sensitive attribute information of a person, such as like race and gender. So for example, here this is a profile information for Douglas and Hope on Twitter. So from this profile information, we can see that there are some words and phrases indicating that Douglas is a male. And with such information, we can actually infer the gender from social media information and then using this kind of inferred information to improve the fairness of machine learning models. So to summarize, so this paper is about measuring and improving fairness of machine learning models. We don't have any information about the sensitive attribute. So the missing sensitive attribute problem is very common in real world data sets such as social media, where we have a lot of training data from Twitter, for example, a lot of we can do a lot of fancy words. But the problem is that as a researcher, we're not able to get any sensitive information, sensitive attribute information like their demographic information such as race, gender, and age, just from social media. So excluding the sensitive attribute during the training process does not solve the problem because in the training features, there are proxies to the sensitive attribute. And if we include the proxies in the training features, the model will be biased. So one solution to this problem is actually to infer the sensitive attribute. So in this paper, we don't use any external proxy variables such as names. And instead, the training set that are used to make train machine learning models will be the same that we use to infer the sensitive attribute of a user. So what are the problems with this hidden sensitive attribute? So this is a typical machine learning model. So we have our training features X, and we are going to apply some machine learning M and get some prediction labels of Y hat. But the problem becomes some features are proxy to the sensitive attribute. So for example, in the previous slide, I showed kind of profile information for Douglas and Hope, that there are some words and phrases in the profile information that are strong indicators of gender of the user. And then those words can be used to infer genders. And then if we actually include those proxy variables in the training features, the machine learning will be biased because it's kind of learning the hidden information from the training features. So next, I will talk about the two datasets we used in this paper. So both datasets were collected from survey responses. We got their consent to link their survey responses to their Twitter handle or Twitter user account, and then collect their tweets. So the first one is predicting the gun ownership status, and then the other one is to predict whether or not a person is willing to take COVID vaccine. Both datasets are textual data from Twitter, and each dataset contains about 600 to 650 Twitter users or respondents. And in both datasets, the gender is the sensitive attribute. And then the gender here, we only have binary gender because the survey is kind of designed for binary gender. So next, I will talk about our overall experimental design. So the first here is to build different machine learning models. In this paper, we have both classic models as well as deep learning models, and I will talk more about them in the next slide later. So next, we are going to evaluate all the models using cross-validation to measure the model performance in terms of accuracy alpha score, and then their fairness score in terms of p-percent and CV score. And then next, we are going to choose the best performing model in F1 score and accuracy in each dataset for the analysis. So after choosing the best model, we then apply 3 external demographic inference models used on Twitter data to infer their sensitive attribute, which is gender in this case. And then apply resampling, pre-processing bias mitigation tool using ground truths and the inference sensitive attribute to get the fixed training data. And then we apply the fixed training data to train machine learning model, and then finally compare the results of fixing methods in terms of performance and the variance. So as I mentioned in the first slide, there are 2 types of machine learning models we use in this paper. So the first one is the classic machine learning models. Those include register regression, random forest, decision tree, and SVM using integrated features. And then the second one is the deep learning neural network model with LSTM layers as well as attention mechanism on the top of first sentence that we evaluate. So we include both classic and deep learning models so that we can have a better coverage of all different kinds of machine learning models that are being used in text classification nowadays. So I will talk more about kind of complexities in some real world data. So one problem in real world data, especially social media, is that it's noisiness. So in Twitter, one problem is that different users have different activity level. So think about this. So someone have a lot of posts, like they're trying to tweet about everything every single day. Though a lot of people don't really post a lot. Like, for example, myself, I really like read things, but really rarely post anything. So in machine learning, in machine learning in general, if someone that only have very few tweets, we're not able to get any good and reliable predictions out of that. So for example, in this figure, it kind of shows the Twitter activity or the number of posts and the sample size. And then in this figure, about 20% individuals have less than 10 tweets in their entire Twitter account. So one of the things we first did was to determine such a threshold for the number of tweets for machine learning model training. So we don't want this threshold to be super low because otherwise we're including people with very like 1 or 2 tweets, and we're not able to get any good or reliable predictions out of that. At the same time, we don't want this threshold to be super high. Otherwise, we'll lose too many samples in the training data. Another thing we want to keep in mind by setting a threshold is that we need to consider the fact that different people use social media differently. So for example, if this is a case that female users are more active than male users in general, and then by setting this threshold, we will filter out more male users than female. And then with this setting, we'll introduce like additional bias to the training data. So the 2 figures on the right shows the gender ratio and ownership ratio across different activity levels. So this is kind of pretty consistent. So when we in the ownership data, so it's like both ratios are pretty consistent throughout the activity level. And then empirically, we determine the threshold to be 10, which is the red dotted line here. And then as I mentioned earlier, like the ratios are pretty consistent. So we're not really introducing any additional bias to the whole problem. So these are the figures for the COVID vaccine acceptance. The distribution is very similar to the ownership data, and the threshold doesn't introduce any further bias. Now I will present results from step A to step C and select the best model in terms of accuracy and alpha score for the analysis. So due to time constraint, I will only discuss the overall numbers, and then we have more detailed numbers in our paper. So overall, classic models have the best performance. So because our data set is relatively small, especially with our whole each data set has about 400 to 450 individuals. So in the non-ownership data, the logistic regression has best performance, and in the COVID data, the random forest has the best performance. So now, after studying the best performing model, we start to improve the fairness using pre-processing fixed method. In this part, we want to first infer the sensitive attribute or gender using the training data. And for this type of inference, we use 3 state-of-art gender inference models that are used on data with accuracies about around 80%. We then use the inverse sensitive attribute and the gradual sensitive attribute to apply pre-processing by conjugation algorithm, and then to get a fair or fix the training data, and then use the fix the training data to train machine learning models, and then lastly compare the performance and fairness of all different machine learning models. So there are 3 types of experiments. So the first experiment is to use true sensitive attribute and the training data to apply the fixing method, and then train a machine learning model. And then the second one is it's pretty much the same thing, except that we use the first sensitive attribute instead of the truth ones, and then do the train. And then the last one is more like a baseline model. It's like we don't apply any fixed method and then directly use the training data to train machine learning models and make their prediction. So here's the result. So on the left figure, left one is a performance in terms of F1 score accuracy, and on the right we have the CD and P% group. So the red squares here are the ones without any fixing. So we can see that it has the best performance in terms of F1 accuracy, but the lowest fairness. And then the purple triangle here is the one fixing with a functional sensitive attribute. So it has the worst performance, but the best fairness. So there's a kind of trade-off between the two, but this trade-off is really small. So for example, in the accuracy perspective, the difference is like 2-3%. So it's kind of small, but if you're talking about the fairness, is kind of huge change. And then for the ones using the inverse sensitive attribute, are really detailed. So we found the result. We found out fixing using inverse sensitive attribute is less effective than fixing using the quadratus one, but still achieve much better fairness than without any fix. So the result on the COVID data is very similar. The model without fixing has the best performance, but lowest fairness score, and then the one fixing using quadratus has the worst performance, but the best fairness, and then the ones in between are the same. And then the result is kind of similar, that fixing using the inverse sensitive attribute is less effective, but much better than doing nothing as well. So that's our kind of work. So in conclusion, where we present missing sensitive attribute in social media. So when we use textual data to train machine learning models, the models will be biased because of the sensitive attribute parts in the training features. And then we show that it's feasible and practical to use existing reliable demographic inference model to actually infer the sensitive attribute, and then use the inferred information to the fairness of our machine learning. And thank you very much.
Up for questions? So let's open it up for questions. While people are thinking of questions, I have prepared one. I don't know if you could share about what implications does your paper's findings have for the future research and applications of fairness and machine learning models on social media platforms?
So as I mentioned earlier, like this is a super common problem for missing sensitive attribute in social media for pretty much every single real world data set. Because one of the things like, oh, social media, but also like from the privacy perspective, that we don't want to collect their personal information or demographic information about users. So one of the things is like, for example, in kind of like financial data, it's like you don't really want to collect their demographic information to kind of avoid the bias. But it kind of turns out that ignoring the sensitive attribute doesn't solve the problem at all. And then this is kind of where the result from the paper is like excluding the sensitive attribute in the measurement model training doesn't really solve anything. And then so it's kind of proposing the idea, okay, so this missing sensitive attribute, how can we really to measure the bias, but more importantly, try to correct the model from to and then reduce the bias.
Do we have other questions? Oh, thank you. And maybe we can each introduce ourselves so we get to know each other.
Sure. So yeah, thank you for the talk, Michael, your PhD student at Carnegie Mellon. So yeah, I guess I was wondering what went into the like problem, like why did you choose the like gun ownership and coded I guess like coded prediction / classification task as like benchmarks for both fairness and accuracy, just like but also to other so like other problems in the fairness space, you know, like loan prediction or like recidivism. It's I guess it's not clear to me what the like fairness implications of like whether someone wants a gun or whether someone like wants to share coded information might be relative to like being denied a loan or like wrongly being accused of recidivating. So just wondering if you could share some of the like thought process with regards to that.
Great question, thank you.
So for the data sets, more like one of the data sets because we're very or that is kind of focused on a lot on the like social science or computational social science particular area. So those are the two data sets that we had previously about this kind of super interesting problem. That's this like for example ownership data that's like it's definitely not publicly available, but you are owner and someone's not. So and then same kind of idea for the COVID vaccine. So we're kind of trying to predict some personal aspect of somebody real life. So and then one of the things like we have their Twitter information, so that's why we want to see if it's possible to use their Twitter information or some public data to kind of predict something about kind of a thought or some kind of like ownership and then like, their opinion about COVID vaccine and then like in addition to this machine learning problem, so we also did like a lot of like topic analysis, for example, on their tweets, and then to see what are the topics they want to focus on, and then what are the kind of the difference between the two things, and then it's like as I said earlier, saying it's really about public opinion, and this is something that people don't really talk about in their real life. It's like for example, I said like ownership, and I don't like say, oh, I'm not an owner. And then say I just tell everyone I'm an owner. So this is kind of like one of the things that we want to kind of discuss, and then the problem is that the data sets are really small here, and then we only have like 600 or so individuals with their valid Twitter